Hey everyone, welcome to this video, and today we are going to discuss about the input embeddings inside a GPT-2 model, or basically any GPT model. So before we had talked about the how we create input tokens or how we create tokens for a GPT model using byte pair encoding, and in this video we are going to convert them to into vectors that has really good understanding about the word. So before it was just this token that was derived for every word, like for hello we had some token 1337, but now we are going to teach the model what does hello actually mean. And that, you know learning comes from this WTE and the weight embedding and the weight positional embedding. So we have two weight matrices, one for embedding and one for positional encoding. And today we are going to discuss this. So if we go ahead and take a look at the embedding dimensions, or how does a GPT-2 model encode a word, we can see that there are around 50,257 tokens inside the GPT-2 model's vocabulary. So after byte pair encoding, we get around 50,257 tokens, which then we multiply with a weight matrix that basically gives us a embedding dimension of 768. Uh, so basically what we do is we multiply these 50,257 tokens. Basically whatever token we get, we multiply it with the weight embedding, which is of 768 dimensions, and we get our embedding. I will make this further clear, but for just now you can just understand that there are 50,257 tokens. That was the vocabulary size, and each token when converted to embedding will have a dimension of 768. Moving further ahead, um, so moving further back, if you guys have not seen my video on byte pair encoding, then for a simple summary, we have this hello word, and then we convert this word into a token using byte pair encoding. And now we are going to convert this token into an embedding. So basically this token we are going to multiply with the weight embedding matrix, and that is going to give us, so weight embedding matrix has 768 embeddings dimensions. So there were 768 weights inside the weight embedding matrix, and when we multiply this token with it, we get an embedding. And if you just look at it, for 50,257 words, for 50,257 tokens, uh, each token will have a dimension of 768 columns. Not just columns, like it will have a dimension of 768. So when we multiply this token with the weights, we get our embedding. And the reason we are talking so much about this is because for the GPT-2 model, or for any LLM mostly, the embedding weights are about 31% of the total learning that the model has done. So these are 31% of the total weights of your GPT models. And for 50,257 tokens, when we multiplied with 768 dimensions, we got 38.6 million parameters. For reference, the GPT-2 model has around 127 million parameters, and out of them 38.6 million parameters are just of your weight of your embeddings. So 38.6 million parameters we get for the embeddings. After applying that token into that weight matrix, we also had to add a position to our beloved token, because without the location, like for example, if I have this word the, and I convert it into a token, and then I multiply it with the weight matrix, then I also had to add a position to it. For example, for a sentence, the problem transformers process, the is the first word, so it may have like a positional encoding of 0, but for a GPT-2 model it was a sinusoidal wave. uh, it is just position. You just put a position, like the is like the first position, the problem will be the second position, transformers will be the third position, and we do this after embedding. So this is just positional encoding. Yeah, we just add position to our word, and this is sinusoidal. So what people don't know, what is sinusoidal, these values are derived from the sine function. So the start point of a sine function, basically the sinusoidal function is something like this. So this first point, maybe the will be represented by this, then the problem will be represented by that the some other position on the sinusoidal graph. So we are getting these values from the sinusoidal function, and after the embedding, we add some position to it, that is a positional embedding. Okay, so that was the logic behind it. And the summation, the summary of it is like we have a token vector, we have a positional vector, and then we pass it into our hidden state. After making the token into an embedding and after adding the position, we put it into then it is moved to the hidden state, and then we do a forward pass throughout the entire network. Yeah, then for ChatGPT-2, we have 12 layers, and we just move this 768 vectors vector token throughout, like whole layers. That's what we do. One important thing is, like, I had this confusion for a lot of time. The token embeddings are not your vector database entries. So nowadays, a lot of people are creating vector databases, and you know token embeddings are something similar to it. You take a token, you multiply it to the embedding, and you get a token embedding. But vector database entry is basically, you have a different type of what you can say, a model that creates these vector databases. The idea is pretty much same. You take a token and you multiply it with embedding, and then you just save it into the a vector database, and then ChatGPT can look into that vector database and can answer your questions. But token embedding is not the vector database entry. They are similar, they have the same concept, but they are not the same thing. It is just a little, you get it from like the final state, from the the and the out, when you're going to get the output. Before that, you get this vector database entry. We will cover this further in some video, but they are not the same thing. That's what I wanted to emphasize. And weight tying is also a very important thing. So what is it says, the embedding metrics we use in the GPT's input, the input embedding and the output embedding are just same, just transposed. So you have this 50,257 rows into 768 columns. You just transpose it and you get your output. So for example, if I had to teach it, this embedding in the first and this unembedding at the last are the same thing. You just copy these weights, these 768 weights, you copy them and you just transpose them here, and you just place them here, and you get your word. Then after you get your word, you just do a softmax and find out which word has the most probability, and you get your output. So basically, when you give an input token, you move it through the whole model, then you just unembed it, and you just multiply it with the, so this weight matrix, you transpose it, you put it here, whatever it was taken here, you just give something back. Okay, when you multiply input with the weight embedding, you get an embedding, and when you transpose this embedding, you get an unembedding, and when you multiply your embedding output, the output you get from the forward pass to this unembedding, you get a token. Okay, so you just gave a token in, and you get a token out by just multiplying the transpose of this matrix. Yeah, that is the basic idea here. So I think that is most of it. Yeah, this is the final hidden state, and you multiply it with the unembedding, the weight matrix, but just transposed, and you get a logits. Logits are your predictions, and in this case, apple, cat, banana, world had the most probability, so you just output that after a softmax. And how it learns, how these weight embeddings are learned, are using your, what you call, a back propagation. So people who don't know about back propagation and how is this done, I'm gonna further teach this in the next video. And yeah, this is just a summary for it, and the bridge between worlds. Great. So thanks for your time, guys. I hope you have a great day ahead.